Hello and welcome to this new tutorial and also to this new code section, because as you can see, now we're about to build the MDN part of the MDN RNN model. Indeed, we're done with the classic creation of the RNN. We've just got at the end here the deterministic output by the RNN thanks to this dynamic RNN function. And now we're about to associate it with what we've created here, meaning the matrix of weight output W and the 1D tensor of biases output B, to create this extra hidden layer, which is exactly what we see here or right here, which are the Gaussian mixtures, which will return a stochastic prediction of the output Z of the RNN. And we're going to do this thanks to our 5 Gaussian mixtures. Remember, K-mix equals 5. Because remember, that creates basically 5 separate distributions of the output, as we can see here. And so now what we're going to do is first reshape that final deterministic output that we've just got, and which remember is a 3D tensor of 100 samples in the batch. So this corresponds to the batch. 1000 frames in the sequence, meaning a sequence of 1000 frames representing a part of an episode when we play the game, so that we can catch the time dependencies happening in these successive 1000 frames. And for each of the 1000 frames, we have this output vector of 256 elements, which basically encodes what's happening inside the environment. So you have to understand that the reason why we take these 1000 frames here is just to catch the time-related dependencies of some parts of the game, and all these time-related dependencies are besides encoded by these vectors of 256 elements. Alright, so this is the actual shape of our output, and now we're about to reshape it, because what we want to do now is to, as we've mentioned before, multiply the output by the matrix of weights output W. But in order to do that, since we're going to use that function tf.nn.xw plus b, which will do a matrix multiplication of x here, which will be our output, which will be at the left of the matrix multiplication, and the weight, which will be at the right of the matrix multiplications, plus the biases. And therefore, since the actual shape of the matrix of weights output W is, as we can see, so I'm going to execute this, is, as we can see, 256 by 480, so 480 corresponds to that and out number here, which is the multiplication of out with .kmix.3. So basically it has 256 lines and 480 columns. And therefore, since we're multiplying the output by the left to that matrix of weights output W, well, therefore we need to flatten the output so that it has 256 columns, which will be multiplied by the 256 rows of the matrix of weight output W. And therefore, what we're going to do, right now, since we have 100 samples of 1000 frames, each one being encoded by a vector of 256 elements, which is, I remind, the RNN size, well, what we're going to do is flatten all this. Basically, we're going to take each of the 100 times 1000 vectors of 256 elements and gather all of them in one same huge 2D tensor, where we're going to have 100 times 1000 rows and 256 columns. And these 256 columns will then be able to be multiplied to the 256 rows of the matrix of weights output W, to which then we're going to add the biases. So let's do this. The way we're going to do this is thanks to the reshape function by TensorFlow, which we've already used for our VAE. And so, since we're about to modify the output, well, I'm going to reintroduce this output variable, and now I'm going to modify it by first calling TensorFlow, TF, from which we're going to get that reshape function, and to which we're going to input first what we want to reshape, the tensor we want to reshape, which is of course so far our 3D tensor output. So here we go. That's what we want to reshape. And then we have to specify in square brackets the format of how we want to reshape it. And the trick to flatten, basically we're flattening these two dimensions here, by gathering in one same dimension these 100 samples of the batch times 1000 frames of the sequence length. And the trick to do that is by adding a -1 here, which will basically gather in one same dimension the first two dimensions, and to specify that what we want to gather in that merge of the dimensions are those 256 elements of each of the vectors of each of the 1000 frames for each of the 100 samples, and therefore we'll specify here hps.rnn size, because that's exactly this 256 number here, which is not only the size of the RNN but also the number of elements in the output vector. And you're going to see that by doing this, well, output is now going to have the dimensions we're looking for. So I'm going to execute this, right? I don't need to go back to RNN values. We can just do it directly this way. Here we go. That's our new output. And now let's see its new shape. I'm going to execute this. And here we go. Now indeed it is a 2D tensor of, remember, 100 times 1000 elements, 100,000 elements in total. So that's resulting from the merge of the two first dimensions here, the number of samples in the batch and the number of frames in the sequence length. And of course, we kept these vectors of 256 elements for each of the 1000 frames of each of the 100 samples of the batch. All right, so now we get the right shape, and now we can indeed do this matrix multiplication of the output, which is that x here in this xw plus b function, computing the matrix multiplication of x by the weights plus the biases, because indeed, now we can clearly see it, the output has 256 columns and the matrix of weights has 256 rows, which allows this matrix multiplication of x times w, output times output w. Alright, perfect. So maybe I'll specify somewhere in the course that it's probably better to refresh our memories of linear algebra and especially matrix multiplication, but you'll have no problem finding some quick refresh online, so I'm not too worried. And therefore, let's move on to the next step, which is, well, now that we have the right shapes of the output and the matrix of weights output W and the 1D tensor of biases output B, well, we're ready to make that matrix multiplication, which will create indeed that frame of the MDN output layer, that extra hidden layer, which will give us the possibility to get the stochastic prediction of the output Z. Alright, so let's do this, and therefore we're directly going to go here, and we're going to take all this, just this, so that we can get the right name of the function. And now, well, we're just going to do the same. We're going to modify the output again, because basically what we've just done here, is not only to be able to do that matrix multiplication, this is actually the input of the MDN. It's like what is entering here in this part. This is the hidden layer, and it takes as input the deterministic outcome of the classic RNN, which is exactly what we've obtained here. And now that we've just got the input of the MDN, well, we're going to get the hidden layer, if you want, of the MDN, which we're going to get thanks to that matrix multiplication of the output of the classic RNN, but which is the input of the MDN, multiplied by this matrix of weights output W, plus this 1D tensor of biases output B. And so, as we said, we're going to modify output again, which will now become that hidden layer of the MDN. And this is now that I have to paste what I've just copied in the TensorFlow documentation. Let's close the parenthesis, and now let's input the arguments. So let's see. I don't know the TensorFlow functions by heart. I always look at the documentation. So this is like I'm coding something new with you. So the first argument that it takes is x, which is of course our output, the output of the classic RNN, which is also the input of the MDN. So here we have to input, of course, first output, good. Then it's going to be so easy. The next argument is the weight, and which is, of course, that output W matrix of weights, which we've created before in the RNN scope. So pasting that right here. And then, of course, very easily, we're going to input the last argument, which is this 1D tensor of biases. 1D tensor of biases, which is of course, well, output B. So this is going to be what comes after the plus, output B, which of course must have the same number of elements that we have here, because this, the number that we need to have for the matrix multiplication, but then this is what needs to be aligned with the biases. So if we select this output B and execute it, we should have indeed 480 as the number of elements of this one unique dimension. So this is all good. This all makes sense mathematically to compute this. And therefore now we have this hidden layer of the MDN, that is this part exactly that we see right here. The MDN part, the hidden layer between the input of the MDN, which is the output of the classic RNN, and the stochastic output or stochastic prediction of Z, which is our final output and which is what we're about to get right now. And the way we're going to get it is through another reshape, because indeed if we execute this now, well, you're going to see that the shape of the output has changed. Here we go. Now I'm going to select this and execute. And now, of course, the shape of the output has changed from a 2D tensor of 100,000 rows and 256 columns to a 2D tensor of 100,000 rows and 480 columns, of course, because that results from the matrix multiplication to which we added the biases. And now what we're going to do to finish this is very similar to what we did here. So I'm just going to copy this, and right here just below I'm going to paste it. And here we go. So we're modifying again the output by taking the previous output, which is this output here, which is the hidden layer of the MDN, and that at this stage had a 2D tensor shape of 100,000 rows and 480 columns. And now we're about to reshape by just replacing this hps.rnn size by kmix times 3. And we'll get that final stochastic output of the MDN RNN, but then we'll get the MDN coefficient in the next tutorial. But before we get to it, well, let's execute this again to, have a final look at what we've created, that final shape of the output. Here we go, executing this. And now I'm going to select this, execute it. And indeed, we have created this 2D tensor of the output with all these number of rows, each one getting the number of mixtures times the number of actions. That is 5 times 3, 15. And that's exactly the shape that is expected in the full world model in that specific MDN RNN part. So that's why I wanted to show you this. This is exactly the shape that we need for the full world model. And now, just before we move on to the next tutorial, let's keep in an object variable that last state, which was returned to us by the dynamic RNN function. We're going to put that in a final object variable, which we're going to call self.finalState, and that will be equal to, of course, last state. And now we can move on to the next tutorial to compute the MDN coefficients, and we'll do that inside a function. Until then, enjoy AI.